Good morning, everyone. Thank you for being here, and my pleasure to present after this group of excellent speakers covering a lot of aspects of 3D printed concrete. We've been working in the area of 3D printed concrete for the last 4 or 5 years. Today, I'm presenting something little different that we are exploring on changing some of the materials. Some of the speakers touched upon a lot of the interesting and the most important things happening today, trying to use the material for structural applications, trying to look at the different microstructure of the material. One of the aspects, as you know, ACI is looking at, and nationally and internationally, there is interest in, is reducing the carbon footprint. And as many of the speakers have shown on their mixes, typically achieving materials like for 3D printed concrete has been happening with a relatively large cementing content. So this is one of the aspects we are looking at. I have some limitations in what I'm presenting because some of the materials I'm presenting is under being patented. So just bear with me if I'm not giving all the details. But my presentation basically is about sustainable 3D printed concrete for sidewalks with low heat storage. I'm going to talk a little bit about the goal and the hypothesis of what we have, some about the using 3D printing as emerging technology, the variables and the rheology of 3D printed concrete. Then we'll talk about the idea of using 3D printed concrete for sidewalks with low heat storage, and about some ideas of producing negative carbon footprint concrete, and can we print it? And then we'll wrap up with some conclusions. So our goal really is to engineer 3D printable concrete with low carbon footprint and still maintain the improved mechanical and durability characteristics, leading pathways to sustainable infrastructure with carbon neutrality. So trying to use the advantages that other colleagues spoke about and the challenge keep overcoming these challenges for producing 3D printed concrete, but also look at the issue of the carbon footprint. We believe that using some of the nanomaterials, especially with the work on nanotechnology for the last 10 years, and 3D printing technology, we might be able to create a new generation of this concrete with good properties and a reduced carbon footprint. Looking at 3D printed concrete, this is an interesting curve that was developed a number of years ago, and it basically look at emerging technologies. And this is known as the Gartner hype curve. And you can see, interestingly, in it, there is a number of other technologies we are trying to show, but there is 5 main steps for any emerging technology like 3D printed concrete when it appears in the market. There is the innovation trigger. There's some innovation, something new happening, some new materials happening. A lot of people are working on it. That is usually followed by what we call as the inflated expectations. So there is way more expected of the new technology than what we can really deliver from. And that follows by what we call as the trough of delusion. And then there is the slope of enlightenment and plateau of productivity. And that's what matters. Why? Because you want the technology, some technologies goes to that peak and then they don't deliver. Really, they cannot be delivered, or they do not deliver as expected. Other technologies continue on after this and gain more knowledge from the needs, from the challenges many of the speakers today spoke about. And then they keep going and keep developing until there is really a plateau of productivity. I'm showing a couple of technologies that we all have seen in the reinforced concrete structures and in concrete in general. One of them is carbon fibers, appeared in the early 1950s. And used for aerospace, then came to the concrete industry by 1980. Today, we are talking about a new code that's coming for using carbon fibers in concrete. That's by ACI. So it is really in the plateau of productivity, and it became a material that any engineer use. Today, the presentation by ERDC showing the challenges. We need to use the design, the material. We are looking how it fails. And we don't know. A lot of the speakers today spoke about the different modes of failure of this material and issues that we are still a lot to deliver on for this technology to develop. Fiber optic sensing is another technology that is coming up and actually started from concepts, and today is available for use. 3D printed concrete really is on the lab scale is just going up. Yeah, on the graph, you see the interest, you see the sessions we have, and a lot of researchers and funding in the area. In the larger scale, really very infant back here down, and we just still starting. So there is a lot of expectation of the materials and the technology, and we are still very early in it. The concept that many speakers talk about is basically we have a design shape, and then we take this into slicing that design and transferring into a code, and then you use this robotic systems to do the scaling and printing. We're showing here some work we've done similar to what some of the speakers spoke about printing, making cuts for cubes, testing them in multiple directions, trying to correlate the properties. And we also showed, like the speakers, that actually there is a very large anisotropy in this material. And then after this, moving from the small scale into a large scale printing. We looked at what are the factors that affect 3D printed concrete as a material. So we developed this nice model. We like to call it the tetrahedral model, similar to the silica model, so that it has a base and then goes up to the hardened properties. And the base basically is these three variables or three key variables: the materials, including the binders you are using, the aggregate you are using, the rheology modifiers, the additives, including the printing process, mixing, pumping, and the extrusion system, the rate, the nozzle speed, the vertical buildup, and then the mix design we are doing, including different aggregate binder ratio and particle size distributions. So all of those together contribute to the middle stage, which is the rheology and the green strength. Also, some speakers yesterday was presenting work on green strength of concrete, which is the strength of that fresh material so that it can be able to withstand the different layers. Viscosity, yield stress, structure relation rate, thixotropy, and green strength are key properties we could observe, and we could put standards, and people are now putting standards on this, so you can actually come up to the hardened properties of interest, including the key one, we believe, is the interlayer and the interfilamentous shear strength. Because if these, and some of the discussion today was about the overlap, trying to improve these properties to make sure that we're not going to have interfilamentous failures. Then the compressive strength, bending strength, time-dependent properties, and long-term durability, which is still long to be looked at because we do not have a lot of these materials tested in full scale yet. But interesting, before I leave this, is that the printing process is a key effect of the material properties that is different than what we used to do with the typical concrete. Now, this printing process and its different parameters can make a big impact on the mechanical properties and the properties of 3D printed concrete. Conceptually, basically, one of the key factors we are looking at is this green strength, and we are looking at how the materials start from being blazed, where you start having at a time, we call it T sub 0, the time you blaze the material, the static yield stress of the material, and how the material through its thixotropy, which is the property of the material based on its mixed proportions and the different materials you have, how that change and how the static yield stress changes with time to TST node plus delta T, which is the time you need to print. As you come to this point in the printing layer up again, and how this affects the stability. And when we look at the stability and this typical equation used, this is only used for the case of strength governing effect, while there is other governing effects other presenters showed, which is the buckling problem, that has become as a structural effect during the building of the material. We show here the typical yield stress change of the material because of the change in the weight, basically placed on the material from the different layers, and comparing it to the static yield stress at time T0 and time delta T, and the growth of that stress and the growth of the strength. And this is a typical relationship always used is the looking at the static yield strength and the change in the strength of the material with time compared to the increase in the stress as you're building different stress. And again, we can use this equation to actually, I think I'm going in the wrong direction. Can use this equation to predict or calculate the required thixotropy of the material, assuming again that the strength of the material is going to be the governing factor. And again, you will not have the structural collapse due to buckling of this material. So using this concept, we were looking at, can we use 3D printing for sidewalks? And the idea here is the issue of the heat storage is that when concrete with materials that can have high heat storage absorb a lot of heat during the day, this concrete will be exposing this heat out in the evenings. So if we can use materials with low heat storage in the concrete, we actually can create a lower heat of the material and to design sidewalks that can be built. Some of those materials with low heat storage, including materials, recycled materials, less energy and less carbon intensive materials. So our interest is looking if it is possible to identify more durable and environmentally and sustainable cost-effective material for concrete, and can we 3D print it? One of the reasons we looked at the sidewalks, by the way, is that there is the strength demand on sidewalks. You know, I believe that we can print sidewalks or we can make sidewalks with strengths in the 1,000 to 2,000 psi. You don't really need a very high strength concrete. So sometimes we say the standard 3,000 psi concrete is good for the sidewalk. Actually, it's very strong. You might not need this much cement materials. And if you see what is the main problems in sidewalks, we see is shrinkage cracks. So if we actually can reduce the cement, we might actually have sidewalks that is more durable and more sustainable. The concept was, again, is that the incoming heat is absorbed through, there is 3 parts, the absorbed heat energy, the radiated heat energy, and the energy conducted through to the soil in the concrete. And if we can reduce the amount of the absorbed heat energy inside the concrete, then the amount of radiated heat energy later will be less as well. This is just a picture of some of the instrumentation we're doing for this 3D printed concrete sidewalks samples we are printing. Of course, if you are going to use it for sidewalks, you will need to finish it at the top after printing. And to measure actually the thermal energy of it. One of the key materials we are decided to examine in this is carbon black that is sequestered from carbon dioxide. So it's not the typical carbon black. There is a lot of recycled carbon black that you can use, and which is valuable as well. You can use from recycling of the tires. But actually here, we're talking about the use of carbon dioxide with methane to produce solid carbon black. And this is work done by a specific company using their technology. And it's a multi-step process where the reactants between either hydrogen or methane with carbon dioxide can produce a high quality solid carbon black particles. So in doing this, in using this carbon black, this is actually sequestered CO2. So you're actually using a material that you can store that CO2 inside the concrete. So this is the specific gravity of this carbon black material, and some scanning electron microscope of those carbon black particles. We decided to start with a simple, this is the simple concrete mix, and you can see one of the items we decided in the standard concrete mix, even without the carbon black, is trying to reduce the amount of cement content. This is in kilogram per cubic meter. So we're reducing the cement and we are replacing a lot with fly ash, slag, and silica fume, trying to actually keep the binder fineness content as required for 3D printing, but in the meantime, reducing the strength because you actually do not need as much in the case for the sidewalks. And our idea was to replace the aggregate with the carbon black. So this is the testing of both the density and the compressive strength with mixes, including up to 30% carbon black. And you can see there is almost no difference in either the density or the compressive strength. So again, a lot of this testing is preliminary, but we do not see in the carbon black mixes any reduction in the compressive strength. So we actually, and what we did, we replaced it here with aggregates. Our next step is actually to replace it with also part of the binder, cement binder specifically, because we already have large content of slag and of the fly ash, which can be used for providing the strength required for the sidewalks. This is a video, but I do not know if it's going to work or not. I don't think it's working. Showing you the printing. This is two different types of mixes here. One with a low content of carbon black, and it also have some rubber crumb particles in it. And the idea of using the rubber particles is to reduce the modulus of elasticity and to actually increase the fracture toughness. We also published about this before. So rubber particles can be between fine and large particles, usually in the same nominal maximum size and size distribution of the aggregate. And the other one is basically, you can see it a little darker. This is basically including about 20% carbon black in it, replacement of the aggregate. This is the calculation we have for the carbon footprint. And this calculation is a standard calculation for carbon footprint, assuming that you have 1 ton of CO2 for 1 ton of cement when you calculate the mix. But here, what we are showing as negative carbon footprint, because with the large change of the aggregate with the carbon black, this carbon black coming from sequestered CO2, so we can consider it as negative. That's why we are showing it as a negative carbon footprint. The calculation is simple also about how much we can really store with this. So the amount of concrete, I'm just making some basic, based on basic knowledge information. There's about 10 billion tons of concrete produced in the United States every year. Assuming that a typical concrete mix by weight, which is about 70% of it is about aggregate, yeah? And that if we can replace with the numbers we are doing our testing on, between 10 to 30% of this aggregate with the CO2 sequestered carbon black, the 10 billion tons will include about somewhere between 0.7 to 2 billion tons of the solid CO2 sequestered carbon black. The manufacturing of this carbon black showing us the manufacturer that they use about 3.7 tons of CO2 to produce 1 ton of the solid carbon black. So that basically would translate that if we are for the 10 billion ton of concrete, we can actually use about somewhere in the average about 5 billion ton of carbon CO2 of this CO2 sequestered carbon black in it. And producing concretes, again, in the typical strength range between 3,000, 4,000 PSI, and it being 3D printable. So this is, again, our 3D printing. Some of the testing we are doing, we are measuring the thermal conductivity. So we are replacing these 3D printed slabs into a sand or a soil specimens that is 1 foot deep, and we are adding thermocouples, and we are measuring basically the heat that it absorbs during the day and the heat it emits in the evening, comparing it to our mix, not 3D printed, and to the standard sidewalk concrete mix, which is again 4,000 or 5,000 PSI, that's having a lot of cement. And again, we use this schematic for the solar irradiation testing setup to measure the irradiation. Again, a lot of this is ongoing as we speak. So to summarize, conclude what we've presented, carbon black sequestered from CO2 has been investigated to be used for 3D printed concrete. Concrete mixes incorporating this solid carbon black particles showed compressive strength is in the 4,000 PSI or 30 megapascal, which is very suitable for concrete sidewalks. I still think it's too high. So we actually can go lower. I think something in the 15 MPa, 2,000 PSI is far enough for sidewalks. The carbon black tends, one of the challenges we've seen, it tends to retain water, which when the material tends to retain water in 3D printing, then the thixotropy of the material will change as you are printing, yeah? and the material printability will change. So we are handling this with admixtures, but more research and work we are doing on addressing this issue, changing the mix so that it would be able to handle this amount of carbon black. For applications with low strength, as I said, replacing part of the cement, that's the next step. We believe because the carbon black here we are using is high fine material, if we replace the cement, that would help us also on the water management in the mix. The changing cement and pozzolans with carbon black rather than changing the aggregates. Thermal properties of the material as being measured, preliminary data showing us actually that we have the concrete with carbon black have low heat storage compared to the concrete, conventional concrete. And as we are adding more of the crumb rubber materials, that heat storage actually drops more. Other important properties, of course, when you have a mix like this is to look at shrinkage. Because that's a key issue in the sidewalks, and of course, freeze-thaw durability and other testing. Some of the work we've been doing in this area for the last few years, I would like to acknowledge the funding by EPA, who is funding this project, and with a number of other companies that's been in the San Diego National Lab and Los Alamos, who's been funding our work for the last few years. Like to acknowledge the work by the research team who actually does this work, and I just use make presentations and take credit, so they deserve the credit. And also, I'd like to acknowledge my colleague, Dr. Greg Rwangold from University of Vermont, who's been partner with me on this work for EPA. And I'd like to thank all of you, and I'm looking for any questions.
Thank you. I think we can take a couple of questions. Okay.
Simple ones.
We have a question for one of our viewers. He asks, 10B tons is total concrete, not for sidewalk concrete?
That's correct. Yes, it's not sidewalk only. One of the issues, of course, once you start replacing materials like this, that's a good comment. I'm just showing the size if you use a large amount of concrete and replace aggregate only by carbon black. But one of the big issues, of course, if you start to do this is to look at, in addition to structural capacity, time-dependent properties. Because when you add materials like carbon black and such, the time-dependent, especially creep, and things like this could affect the structural capacity of concrete.
I think this is a truly innovative work. I really love your approaches and how the sequestered used. Congratulations. So I was wondering for the roofs, have you thought about coming up with a similar approach, not only the sideways, but for the rooftops?
Yeah, that's a good idea. Again, of course, it could be used for roofs, for anything that is heat storage in it is necessarily, and the strength demand is not high. That's why we directed our work to sidewalks, because of the fact that we do not need a lot of strength there, and we need the issues of heat storage is big. You are absolutely right. I think it could be also used for, there is no limit on the application. It's the limit will be what mechanical properties and our printability of this concrete.
And also I wonder about the longevity
yes.
of these sideways.
Absolutely. We are still very preliminary. We're just starting on this, but I agree. One of the things we think, if it's sidewalks, freeze-thaw has to be examined because if it's lower, then it's a problem. So we did not test any longevities yet.
Thank you.
Thank you.
Thank you for very interesting topics. And yeah, we agree that the 3D printing material has kind of high carbon footprint in general. And you pointed out that is kind of type of research interest in going forward. Is there any specific reason that you choose 3D printing versus cast in place? Because we can do in cast in place like this way, and yes. Any specific reason for your background of your research about 3D printing on this?
That's a good question, a very good question, actually. Of course, the general interest is to be able to use this material in concrete. Yeah, concrete with the, as we said, low strength requirements and high heat issues. The reason we've been involved with, as I said earlier, in 3D printed concrete. And one of the areas that came as a discussion with a group in New York actually was that can use 3D print sidewalks. So the idea of 3D printing of sidewalks have been around because again, with the printer and the ability to print quickly, then you can print these sidewalks and the thicknesses requirement make it very amenable and easy to be done. So that is where the idea we have about using the carbon black with concrete we added to our work on 3D printing. But it definitely can be used for non-3D printed concrete. It actually might be easier because, as I said, we have a number of challenges related to the buildability and printability because the material, water changes with time. If you make a mix that does not require this printing, you might be able to do it easier. So there is no specific reason why, but that the discussion we have with some contractors about 3D printing of sidewalks.